Our first speaker this morning is Laslo Babai. He is a professor of computer science and mathematics at the University of Chicago, and he will talk about symmetry versus regularity.
Thank you. Actually, I'd like to invite you to come a little closer. I don't bite. Okay, so, yeah. Okay, so that's the title, and I can't see what I'm doing here. Good. Okay, so regularity is something that you define in terms of numerical parameters, and symmetry is defined in terms of automorphisms, transformations that preserve the structure. And so it is clear that symmetry always implies some sort of regularity, but not the other way around. So, for instance, I mean, here is an example where actually the opposite happens. The dodecahedron is defined in terms of regularity. I mean, we just prescribe what happens in every corner, and somehow magically then it folds up to something that actually is symmetrical. It has automorphisms. So, but that's a rare thing, and the reason that this way we can also infer from regularity, we can infer symmetry is because from regularity, the condition is so strong that we can classify the objects that are defined by our regularity constraints. And of course, then we can inspect every one of them and just observe that it actually has the symmetry. And one of the questions I'd like to look into is really this step necessary for this kind of inference? Okay, so symmetry has often has very strong structural consequences. And one of the questions that I'd like to look into is whether one can relax the symmetry assumption to regularity conditions and still make similar inferences. There is a paradox of symmetry. There is a trade-off between the quality of symmetry and the quantity of symmetry. Quantity of symmetry would just be the number of automorphisms. The quality of symmetry, that's something that is evident when you look into what kind of symmetries we consider. But in any case, what seems to be rather easy to observe is that higher degrees of symmetry force fewer symmetries. Question then, analogous question, if we only assume regularity, does that impose such a constraint on the number of symmetries, on the number of automorphisms? Okay, and then, of course, this is the big question. Is it possible, at least in some contexts, to infer symmetry from regularity without passing through classification of the objects that satisfy the regularity constraint? So it should be a regularity constraint that still allows a sufficient variety of objects to satisfy it, that classification remains hopeless, and maybe nevertheless we can infer symmetry. Okay, so the challenge is or at least one of the challenges is that consequences of symmetry are usually proved by group theory and often enough with heavy machinery and possibly involving the classification of finite simple groups. Whereas when we have only a regularity constraint, the group theory machinery is not available to us. And so what can we use? I mean, combinatorial ideas and linear algebra, presumably algebra of all sorts and number theory could be useful. In the examples that I'm giving, really combinatorics and linear algebra play the main role. Okay, so now, why are we looking into these questions? Well, first of all, most regular objects of the kinds that I'm going to define that are being considered in combinatorics, especially in algebraic combinatorics, are not symmetric. So this means a vast increase in the scope of the results. Another thing, from an algorithmic point of view, regularity is a local thing and it is easy to verify. And symmetry is not. Symmetry is global to the entire structure and for instance, verifying that a graph has a transitive automorphism group, this is not known to be doable without solving the isomorphism problem. So this distinction is critical to algorithmic application. In fact, the entire graph isomorphism problem is just about moving from regularity to symmetry. Regularity we can get very easily, and symmetry is what we wish. Yes, Boaz?
Most objects are also almost regular. Your application is regular
No, it's very strict. Yeah, so I am not looking at polyhedra that have almost the same number of sides, and it has to be exact. Yeah. Things become a whole lot more difficult if I allow little deviation from this, because then the group series structure is lost. Okay, so okay, as a byproduct of such proofs, one also gets a benefit even if there is a symmetry assumption there. Namely, we are forced to use elementary means, at least not the classification of finite simple groups, and that definitely gives new insights even under the assumption of symmetry. Most of those who use the classification of finite groups, they use it as a magic box. And that's not the way we used to do mathematics. We like to understand it from first principles, if possible at all. So I use myself the classification often enough, and there is nothing better to do. But it's unfortunate, and I would like to advocate this as a valid purpose in itself, to give proofs that we understand from beginning to end. Okay, so a quick introduction to permutation groups. So here is some notation. The symmetric group acting on a set omega, which I call the permutation domain, that's denoted like this. If I don't want to specify the domain, only specify how many elements it has, then it is denoted by S sub n. The alternating group is half of this, consists of the even permutations. The notation will be the operators I write in the exponent. So if x is an element of the domain and sigma is a permutation, then x goes to x to the sigma. A permutation group is just a subgroup of the symmetric group. The less than or equal sign in this talk will indicate subgroup, unless it is between numbers. So the degree of the permutation group is the size of the domain on which it acts. The orbit of an element is the set of all images of that element of the permutation domain, and the group is called transitive if the images of one element cover the entire domain. Of course, then it doesn't matter which element. The group is doubly transitive if it's transitive in its induced action on the ordered pairs of elements. And we are looking at all sorts of induced actions. So when a symmetric group permutes our permutation domain, it also permutes all sorts of derived structures. One of the most important of those will be action on t-tuples of unordered t-tuples. But this is ordered pairs. That's doubly transitivity. Okay, so doubly transitive groups are essentially known. There is some dispute over whether or not those which are affine, so they work on a vector space, whether they are exactly known. But as long as I only want to know, want an upper bound on their order, the affine case is trivially bounded by this, so it is enough for us if we know the non-affine ones, which are related to the Lie-type simple groups. And Curtis, Cantor, and Seitz, well before the classification of finite simple groups was first announced, they already, under that assumption, classified all doubly transitive permutation groups, and from the classification one can see that they have at most disorder. This is actually not even an asymptotic inequality. Most of the time when I say an inequality like this, what I mean is for all sufficiently large n. So this is true for n at least 25 to rule out the Mathieu groups which violate it. Okay, so now what can one do without the classification of finite simple groups? Well, Piber and I divide some combinatorial methods with which one can get close to this. So this is exponentially in log squared then, and Piber was able to prove log cubed of an upper bound for all doubly transitive permutation groups other than Sn and An. Okay? So this is a striking example that we are improving the quality of symmetry. The permutation group describes symmetry of something. We improve the quality. Doubly transitive is somehow more homogeneous. It's a more symmetrical structure. And all of a sudden, from n factorial, it goes down to quasi-polynomial. I'm going to use this expression quasi-polynomial. So the exponent here is a power of log. We call that polylogarithmic. And exponential in polylogarithmic is called quasi-polynomial. So these groups are bounded quasi-polynomially. So they are really tiny compared to what a permutation group could be. Okay. So now, all right. is it more than just really a nice, aesthetically pleasing thing that we can prove this without the classification, or is it good for something? Yes, these extra insights, these were actually recently used in a breakthrough result by Helfgott and Sheresh, who proved that the diameter of the symmetric group is quasi-polynomially bounded. Now, the diameter of a group means that we look at any set of generators, and we look at the word lengths, the lengths of the words that describe every element of the group in terms of those generators. We look at the maximum word lengths over all possible elements to be reached and over all possible sets of generators. So we look at the worst generators and then the largest diameter, and even that is bounded by this. The conjecture is that it is actually polynomially bounded, and no set of generators is known where it would not be quadratically bounded. So the gap is still large, but the previous best bound was exponential in square root of n. So, okay. Okay, graphs. So I'm going to talk about graphs. So this is a graph. Okay, graph is nodes and links between them. So the nodes are called vertices and the links are called edges. If V is a set, then V choose 2 is going to denote the set of unordered pairs. So the set of vertices this is V. Set of edges is a subset of V choose 2. So it is a set of unordered pairs. These pairs are called adjacent. So adjacency is an irreflexive and symmetric, I forgot to say, binary relation. Okay, so the degree of a vertex is the number of its neighbors, and we say that the graph is k-regular if every vertex has exactly k neighbors. So for instance, this is a famous 3-regular graph. Every node has 3 edges leaving it. It's called the Petersen graph, and it is immediately not evident if you look at the picture that it has relatively a huge automorphism group. What is obvious from the picture is that it has at least 10. It has the symmetries of the regular pentagon, and with some more work you can also prove that you can switch the inner and the outer pentagon, so then that gets you 20, and that's still far cry from the 120 that it actually has. So the symmetry is somewhat hidden here. Okay. Now, let's look at an example of a more direct example of the symmetry paradox. So if a graph is vertex-transitive, which means that the automorphism group acts transitively on the set of vertices, okay, that's still, okay, so that's what vertex-transitive is. And arc-transitive means that it acts transitively on the set of ordered pairs of adjacent vertices. So in particular, every edge can also be reversed. This is part of the condition. Now, if I have a vertex-transitive graph, a connected vertex-transitive graph, it can have exponentially many automorphisms. Imagine this is a wraparound picture, so this will somehow close up. This is the crossed ladder, and you can see that if you look at these 4 vertices here, these 4, okay, then you can simply swap the upper 2 and the lower 2. And you can do this independently everywhere, so that gets you 2 to the n to the n over 4 automorphisms already, and then you can also shift them, so that's a factor of n over 2. So in any case, this is exponentially many, and this graph is vertex-transitive. If we strengthen the condition of vertex-transitivity just a little bit to make it arc-transitive, then there are linear number of automorphisms at most. So Tat proved in 1947, and everyone wonders why he proved it, that an arc-transitive graph, which is 3-regular and connected, has no more than 32 times n automorphisms. It's an amazing result, and there has been a lot of work to generalize this. Okay, now let's look at another type of structure. So I will have to mention a lot of structures because this entire talk is largely about examples and then questions that are raised by the examples. So an incidence geometry is a triple where the first member of the triple is called the set of points, the second is the set of lines, and the third one is called an incidence relation. Okay, so when a point and the line are incident, then they get into I. A case of these are the Steiner 2 designs, where V and K are the parameters. V is the number of points, and K is the length of each line. So this means the number of points incident with each line. So this is a uniform system. Every line has the same number of points, and there is a geometric axiom. The geometric axiom is that for every pair of distinct points, there is precisely one line passing through them. So that's what makes it a Steiner design, and that's what gives it this geometric feel. Okay? Now, if we also have the second axiom that every pair of lines intersects, then essentially, apart from trivial examples, this is what is called a finite projective plane. And here is an example, the smallest example of a finite projective plane. So it has 7 points, 7 lines. Each line has 3 points. So it satisfies this equation n equal k squared minus k plus 1. And that's generally true for projective planes. Okay? Now, again, let's look at possibilities of symmetry. If a finite projective plane with n points has a doubly transitive automorphism group, which every example that I can easily tell you does, then it follows that the number of automorphisms is essentially quadratically bounded, just a little more than quadratically. Okay? And the reason for this is that if this is the case, then Ostrom and Wagner proved that the plane can be coordinatized over a finite field. So what we have is simply the linear group, and the log factor comes from field automorphisms. Okay, so the conjecture would be that this extends to all finite projective planes, at least in the sense that they are polynomially bounded. But what we can prove is that it is bounded by something that grows, however slowly, and log n is in the exponent. And I would be very curious to see some progress on this, but this seems to be currently not tractable. Okay, let's get back to Steiner designs. Okay, so examples of Steiner designs are the points and lines of the d-dimensional affine space, and also of the d-dimensional projective space. So these are the two most standard examples. These have doubly transitive automorphism groups. I mean, we can directly check that the automorphism group is not greater than essentially n to the log n, but also we know separately from the fact that they are doubly transitive. The question is then, what can be said without the symmetry? So if we just assume that we have a Steiner 2 design and we don't assume anything about its automorphism group, well, a Steiner triple system is a system where every line has just 3 points. So this is an example of that, and it is trivial to show that a Steiner triple system has no more than this many automorphisms. The reason is that a Steiner triple system can be thought of as having a binary operation on its base set. Namely, for every 2 points, you assign the third one. If they are not equal, if they are equal, then you just make it idempotent. So that every element times itself is itself. And then you can see that this system is generated by, at most, logarithmic number. Log number of elements, for the simple reason that a subsystem is at most half of what it is. We don't have Lagrange's theorem here, but nevertheless, it's easy to show that a subsystem cannot be greater than half of the original. So there are log n generators, but then if I look at an isomorphism, okay, where do the log n generators go? That extends in at most one way, to an isomorphism, in particular to an automorphism. So the number of images of the generators is at most this much, and that's it. It is far from trivial, however, that this bound generalizes actually to all Steiner systems, and that we proved with my student John Wilmes, and at the same time Shi Chen and Shaori Sun and Shanghua Teng, all of them computer scientists. Okay, if you ask them, are you mathematician? Well, they are first-rate mathematicians, but they call themselves computer scientists. And so that was proved actually in the context of the graph isomorphism problem, but I think that it is far more interesting in this context, in this symmetry versus regularity context. And so this is the result, and that involves substantial structure theory of these rather amorphous objects. So we have an n to the constant times log n upper bound in the general case. Okay, so now there is a pair of concepts, distance-transitive and distance-regular graphs, on which I want to dwell a little bit because they really illustrate this connection between transitive and between symmetry and regularity. A distance-transitive graph is a graph in which the automorphism group acts transitively on pairs of points at equal distance. So if I take 2 points at some distance and 2 other points at the same distance, then there is an automorphism that moves this pair to that pair. That's the definition of distance-transitive graph. And so a famous example is the Hamming graph, which consists of all strings. So with parameters k and s, then it consists of all strings of length s over an alphabet of size k. So, okay, I can write down k to the s words of length s over an alphabet of size k. And these are going to be the vertices of the Hamming graph. And distance in this graph is Hamming distance. In particular, they are at distance 1. They are adjacent if they differ in exactly one letter. So that defines the Hamming graph. The Johnson graph has k choose t vertices, where k and t are my parameters, t is less than half of k. And so the vertices are naturally labeled by t subsets of a set of k elements, and 2 of them are adjacent if they differ minimally, so if their intersection has size k minus 1. Okay? So that's the Johnson graph. Okay? And then these things have Q analogs. Q analog means refers to doing the same thing over a vector space, over a finite field. So in this case, subsets become subspaces. So we look at the t-dimensional subspace. So I am looking at the analog of the Johnson graph, the Q analog. So I look at, instead of a set of k elements, I look at a k-dimensional space over the field of q elements, and then adjacency occurs when the dimension of the intersection is maximal. So 2 subspaces differ minimally if their intersection has codimension 1 in each. Okay, that again defines a distance-transitive graph. So all these graphs satisfy this very high degree of symmetry. Okay. So let me talk a little more about the Johnson graph. So the Johnson graph again has the t-tuples of a k set as its vertices. And then what are the automorphisms? It is obvious that the induced action of the symmetric group on t-tuples is part of this automorphism group. And in fact, it is equal to the automorphism group. This is something that was shown, I think, about 40 years ago by Kaluzhny and Klein, and probably a lot of other people who didn't know about Kaluzhny and Klein. So the Petersen graph, which is the most famous of our graphs, is actually the complement of the smallest non-trivial Johnson graph, and that here is a proof that its automorphism group is isomorphic to S5. Okay, this is a nice exercise for a class if you happen to teach graph theory and you have students who are up to talking about automorphism groups. Okay, so what's a distance regular graph? A distance regular graph tries to extract some combinatorial consequences of the symmetry and make that as axioms. Of course, there are infinitely many consequences, and what we pick depends on what we find most natural. So here is what seems to be the most natural. We look at the metric. So these different colors denote different distances within the graph, and the condition is if I have 2 pairs of vertices at some distance, this pair, and blue denotes that distance, and I specify 2 other distances, red and green, then the number of third points that are at red distance from x and green distance from y doesn't depend on the particular choice of x and y. It only depends on the distance between x and y. Okay? So that's the definition of distance regularity. So this is obviously a consequence of distance transitivity, and however, the converse is not true if I have a distance transitive, if I have a distance regular graph, so a graph that satisfies these regularity conditions. It may even not have an automorphism, a non-trivial automorphism at all. There are, in fact, large families of distance regular graphs that have trivial automorphism group. Okay, so let me talk a little more about strong irregular graphs. So a strong irregular graph is usually described in terms of 4 parameters. N is the number of vertices. The graph is regular of degree k, so every vertex has k neighbors. An adjacent pair of vertices has lambda common neighbors, and a non-adjacent pair of vertices have mu common neighbors. So for instance, if you look at the pentagon, which I failed to draw here, it has 5 vertices. Every vertex has degree 2. Adjacent vertices have no common neighbor. The graph doesn't have a triangle. And non-adjacent pair of neighbors has exactly 1 common neighbor because it doesn't have a quadrilateral. Petersen's graph has similar parameters. It has degree 3, and lambda and mu are the same. Okay? There are other graphs of interest, especially the line graph of the complete graph. So if I take the line graph of a graph, then the edges become vertices, and intersection becomes adjacency. So if I take the complete graph or clique with v vertices, so that's v nodes and every pair is adjacent, that means I have v choose 2 edges, and so in the line graph there will be v choose 2 vertices. And now adjacency means that the two edges meet, and one can easily calculate that this is going to be a strongly regular graph, and one of the most important examples we have, because this is going to be a Jones-zone graph. So this is a Jones-zone graph with parameter 2 at the end, and so that's why it has v choose 2 vertices. Line graphs of affine projective geometry. So again, here the lines of the geometry are becoming the vertices, and the intersection is going to define adjacency. Out of number theory, we often encounter the Paley graph. It has q vertices, with q is an odd prime power, well, okay, it is a graph if it is 1 modulo 4, and 2 vertices are adjacent if their difference is a quadratic residue in that field. So that's, again, a strongly regular graph. So there are lots of interesting families of strongly regular graphs. Actually, the strongly regular graphs are exactly the distance regular graphs of diameter 2 if I ignore trivial cases that are disconnected. A disconnected strongly regular graph is simply just a union of disjoint cliques of equal size, and everything else is distance regular and has diameter 2. Okay? All right. So Peter Cameron and I proved long ago that there are about n to the n over 2. So about factorially many strongly regular graphs with n vertices that have no automorphisms at all. In fact, this comes out of Steiner triple systems and Latin squares. I didn't define them, so let me talk about Steiner triple systems. So we look at the line graphs of Steiner triple systems. So the vertices of my graph are going to correspond to the lines in the Steiner triple system, and adjacency corresponds to intersection. And so what we have shown is that almost all Latin squares and almost all Steiner triple systems with at most n points have no automorphisms other than the identity, and this is inherited to the line graphs with just a few exceptions, and so we get large families without automorphism. Actually, yeah, all right, so these all have, so now I indicated that we can construct large families of asymmetric, strongly regular graphs, but I said, okay, so distance regular graphs, well, they are distance regular, however, they have diameter 2. And it is an open question, as far as I know, that whether or not there exist distance regular graphs of large diameter that have no automorphisms. I find this a fascinating question. If this fails, then the examples, it would be a stunning set of examples where the regularity assumption implies symmetry. On the other hand, I don't believe that it fails. But if it doesn't fail, that means that we are woefully short of methods to construct these types of graphs. We are not even close to getting something that has no automorphisms. In fact, all of those that we know are either vertex-transitive, or at least they only have 2 orbits. So they are very symmetrical, and so that is a tantalizing open problem. Okay. So, yes, under what circumstances can we infer symmetry from regularity? Okay, so here is a case when we can. Okay, if I have a graph, X, V is the set of vertices, C is the set of edges, and A is a subset of the set of vertices that defines a subgraph on that subset. That's going to be the vertex set, and adjacency remains the same as in the original graph. So the induced subgraph is completely determined by just the set of its vertices. The adjacency is just inherited. So here are 2 conditions now about these subgraphs. A symmetric condition, we call a graph K-homogeneous if whenever we pick 2 subsets of size at most K, and the induced subgraphs on them are isomorphic, then this isomorphism actually extends to an automorphism of the entire graph. So small subsets span isomorphic subgraphs, then one subset can be mapped to the other by an automorphism. Now, a much weaker, seemingly much weaker regularity condition, which I call K-set regular, requires that if I have two subsets of equal size and they induce the isomorphic subgraphs, then they have the same number of neighbors. Now, this is obviously a consequence of the symmetry condition, but it seems so much weaker that one hardly would expect any significant consequences out of that. Now, let's look at what this condition means. If k equals 1, then it just means that the graph is regular, okay? So it means that that's the regularity condition, okay? The number of common neighbors of one point is its degree, so it has to be the same for every vertex. For k equal 2, what this means is the number of common neighbors of a pair of vertices only depends on what that pair of vertices does. It can be either adjacent or not adjacent or diagonal, the 2 points equal. And these are the only three possibilities in a strongly regular graph. This is exactly the family of strongly regular graphs for k equal 2, okay? And then for k higher, we get stronger and stronger restrictions. So what Cameron and independently Killeen and Golfand proved a long time ago was that if a graph is 6-set regular, then actually it is 6 homogeneous. So the regularity condition implies the symmetry condition. In fact, it implies that if it is 6 homogeneous, it is k homogeneous for all k, and so you already suspect how this goes. The way this goes is, yeah, okay, we are happy, we found an example, regularity implies symmetry. Yes, but the actual result says this. If the graph is 6-set regular, then it is one of these. It's either a union of cliques of equal size, or a pentagon, or line graph of K33. K33 is just the three utilities graph, or their complement. So we can list the entire set of these examples, and we find this was out of an assumption of regularity that they are actually homogeneous for every k. And so, well, what we get is the less surprising thing, that the regularity thing implies full classification of our objects, and then by inspection we just find that they are all symmetrical. So this really just illustrates that principle that regularity doesn't really much go in any other way to symmetry. Okay, so I'd like to present something that at least in some sense goes the other direction. We can infer some sort of symmetry out of some sort of regularity without having a hope for classification of the objects we are talking about. And there will be an adjective here. The word is hidden, okay? So in some well-defined sense, I'm going to show that a certain type of hidden irregularity, okay, so if we have that, that's fine. But if we don't have that hidden irregularity, the opposite is not just merely going to be hidden regularity, but hidden robust symmetry. So if that irregularity is not there, if we call the opposite of not regular, regular, then that's a regularity, a kind of regularity that implies some kind of symmetry. Symmetry will be hidden. But it will be absolutely indestructible in a well-defined sense. This symmetric object that will show up in that case is going to be the Johnson graphs, and I'm going to define in what sense we are trying to destroy it, and it will not be possible. So, okay, but before going there, let me discuss distance regular graphs and distance transitive graphs a little more. So here is a major theorem which says that if we have bounded degree under one of these conditions, then the entire thing is bounded. So it's essentially a layering of the entire set. It's stratification. Every degree defines a finite number of such objects. Now, for distance transitivity, this was proved long ago by Cameron, Prager, Saxel, and Seitz. Of course, it heavily uses the classification of finite simple groups, in particular if I have a distance transitive graph, and I look at the stabilizer of a point and look at its neighbors, the action of the group is doubly transitive on the set of neighbors, and so that's, okay, so those are classified using the classification of finite simple groups, and then one can go through the cases and prove the bound, it's still highly non-trivial, okay? But this motivated then a conjecture that became known as the Banai-Ito conjecture, that the same should hold for distance regular graphs. And this was also confirmed, well, a mere 33 years, 1/3 of a century later. And it's no surprise. This is based on a combinatorial lemma by Sasha Ivanov, plus about 40 years of amazing spectral analysis, somehow localizing the eigenvalues of the adjacency matrix and deriving consequences ever more restrictive. So that result is really a tour de force of spectral analysis, and certainly perhaps the most important result in recent decades in algebraic graph theory. So, okay, now let me switch topics and look at another area of mathematics, of combinatorics, extremal set theory. So a hypergraph is just a pair of a set consisting of a set of vertices and a set of what we call edges or hyperedges, but these are now not pairs as in a graph, but arbitrary subsets. So the set of edges is simply a subset of the power set of the set of vertices, and the set of edges we refer to as a set system, and basically we are going to, the set of vertices is not going to matter a lot, so I'm going to talk about set systems or hypergraphs. They will be essentially interchangeable. Now, the set system is called K-uniform if every set in the system has size k. Now, it is called regular if every vertex has the same degree, where the degree again is the number of edges containing a given vertex. So for instance, if I look at a Steiner 2 design, then it is regular. Every point has the same number of lines through it, and it is also uniform because that's by definition every line has the same number of points. Okay. Okay, one type of conditions on hypergraphs that has been studied a lot is intersection conditions. So a hypergraph is intersecting if every pair of edges intersect, and then the celebrated Erdős-Corrado theorem, which was proved in the 1940s and published in 1960 and became a big success at that point, says that if we look at the maximum possible, that's what extremal set theory does. Impose some condition on the hypergraph and then look at the maximum possible number of edges that can satisfy that condition. So the maximum number of edges is obtained by taking one particular point and all subsets of size k that contain that. So that's what the Erdős-Corrado theorem says for uniform hypergraphs. Now this special point has bothered people even before it bothered me, and so they asked in 73, I guess Erdős, Rothschild, Symmetry, I couldn't find the paper, but it is being referred to in Frankel's paper. What happens if we restrict the degree to be some constant fraction of the total number of edges? Okay, so once again, here we have a special point so that every edge contains that special point. That gives the extremal structure, so clearly the extremal number is going to go down if we exclude that. We don't allow a point that would be contained in every edge. And the question then is, what is going to be the structure of the extremal hypergraph? So under the condition that our hypergraph is intersecting and its degree is bounded to a constant fraction of the total number of edges, question is, what does the extremal hypergraph look like? Well, typically it looks like this. There is a small part of it which is a finite projective plane. I didn't know how to draw that little circle in perspective here. So, but imagine that this is a little projective plane down here. And then our set system is the following. Just take every subset that contains at least one of the lines of this projective plane. Such a set system is clearly intersecting simply because the lines of the tiny projective plane are intersecting. So the intersection is all going to occur within this subset. And this is going to be actually optimal in various ranges of the values of k. So for instance, oops, I don't have it here. So anyway, if this constant c is strictly between 1/3 and 1/2, then it is going to be the Fano plane. That's what Frankl proved before Furedi proved it in general, that it is going to be over infinitely many ranges. This is going to be best possible when we put a projective plane there. Interestingly now, this also partly means that the actual optimum depends on the existence question of finite projective planes, which is a big open problem in combinatorics. But again, from our point of view, this is again highly irregular, because the only thing, previously there was one point that was different from all the others. Now this one point is now spread to a small core set. So this also we want to exclude if we want even regularity. Okay, so regularity already is going to affect this problem, because these examples are all highly not regular. But then there is a question, okay, vertex transitivity would of course also affect it, but question is, could it affect much more than just merely regularity? Obviously, regularity is, especially for hypergraphs, is an incomparably weaker condition than transitivity. However, if we look at the extremal set system, maybe the difference is not that big. So that's an interesting question. How big can be the difference forced by vertex transitivity of our examples, as opposed to just mere regularity? And it is Peter Frankl who championed this question. Now, he wrote 2 papers in 1980, and so Frankl's work is quoted all over the place. I mean, he's one of the really masters of extremal combinatorics. These 2 papers specifically received a total of 4 citations, and 2 of them from himself. So this is old news, but it reads like new, and it is exciting reading, by the way. Beautiful results and beautiful methods. Okay, so the first thing is a little exercise. Everybody can solve this. So a little challenge. If I have a k-regular uniform intersecting hypergraph, okay, so every pair of edges intersects, every edge has size k, and it is uniform. I don't even tell you what is the degree. Every vertex has the same degree. Then k is greater than or equal to square root of n. This is something you can prove in 3 lines. It is a little more difficult what Lovász and Furedi proved, that actually n is not just less than or equal to k squared, but less than or equal to this, which is a tight bound then, and the equality is going to hold for projective planes. But it doesn't matter from my point of view, essentially square root of n. So basically what this means is that regularity assumption reduces Erdős-Corrado extremum to 0, because there cannot be a regular uniform hypergraph. Okay, so that really tells us that maybe we should switch to non-uniform hypergraphs, and that's what Frankl did. If I take a non-uniform hypergraph, then naturally I can assign a density to it, which is simply I divide by the number of edges by 2 to the n. So then I get so now an intersecting hypergraph obviously has density at most 1/2, because a set and its complement can never be both members of the set system. Now, however, if we look at 3-wise intersecting hypergraphs already, so every triple of edges intersects, then Erdős and Rado proved that the only extremal system in that case, again, is when you pick one point and everything that contains that. So if I just take an intersecting system, there are many, doubly exponentially many extremal hypergraphs that realize this density 1/2. But if I require 3-wise intersection, then there is only one, and that is this. This special point has twice the degree of all the other points. So if I impose regularity, then that is going to push down the extremum. Now Frankl considered then these 2 quantities. So suppose we look at t-wise intersecting regular hypergraphs. What is the maximum density? That's R and T. And if we say it is t-wise intersecting and vertex-transitive, so every vertex is equivalent under automorphisms, that's T and T. And then the question is, what can we say? How do these densities compare? So the maximum density of a regular hypergraph and the maximum density of a vertex-transitive hypergraph that is t-wise intersecting, and the interesting case now will be when t is at least 3. Okay, so the first thing is, he made the interesting observation that for regular, you can always get, for every t, you can get a constant fraction. So this quantity is bounded away. For every fixed t, it is bounded away from 0. So no matter how large hypergraph we take, if we fix t, a constant fraction of that can be made so that it becomes regular. It will somehow be accidentally regular, so it is not going to be vertex-transitive, and that's no surprise because Frankel also showed, at least for T at least 4, that the proportion of edges in a vertex-transitive hypergraph must go to 0. And he conjectured that this is already true if we require 3-wise intersections. So this required 4-wise intersecting hypergraph, but it is also true for 3-wise intersecting. And the brand new result that gave me the opportunity to actually put it on your screen is that Ellis and Narayanan proved this conjecture. It's a very clever proof, and it ties in with a lot of questions, again, that theoretical computer science has considered. So Frankel proves, for instance, for T5, proves this beautiful upper bound. Somehow he relates this to the golden ratio. So if I have 5-wise intersection, then the exponent, then the decay is already exponential in third root of n, and for 6-wise intersections, it is already decaying in this exponent of square root of n, and basically it jumps at every 3. When the number becomes a multiple of 3, then the exponent gets closer and closer to 1. I very briefly sketched the proof for T6. So let f sub I denote the minimum possible size of I-wise intersections. So if I take I of the edges of the hypergraph, they have intersection sizes, and we look at the minimum possible size of those intersections. And look at the number f3. So f3 is the minimum size of 3-wise intersections, and Frankel has a beautiful lemma which says that the density of a hypergraph, no symmetry assumption here, if this is true for any hypergraph, the density is not greater than this inverse golden ratio raised to the power f3, so this minimum size of the 3-wise intersections. Okay? And now, if we look at the set of all 3-wise intersections, over 3-wise intersections of minimum size, okay, so that's what we are looking at, then this is uniform by definition because all of them that are included here are of minimum size. But it is also regular under our condition. Well, that would be a mystery, but it is regular. Why? Because we assume that the hypergraph is vertex-transitive. So every vertex is alike. No matter what invariant you invent, depends on a vertex, it is going to be the same for every vertex. Okay? And now, okay, we have this exercise from previously. This F3 is an intersecting hypergraph, intersecting because it was 3-wise intersections, but we are assuming the entire hypergraph is 6-wise intersecting. So every pair of 3-wise intersections intersect, and it is uniform. Therefore, F3 is at least square root of n, so we have square root of n in the exponent, and that proves the result. Okay? All right. So this is the general result that Frankel proved, where this T and this S are the same number. No, S is 1/3, right, S is about 1/3 of T, yes. Okay, and I just wanted to show you a beautiful sort of convexity type lemma that he proved. If F is vertex-transitive, then this kind of inequality, subadditivity or submultiplicativity holds for these minimum sizes of the intersections. Okay, so the proof uses the regularity of f of I. Just to see what this says for I equal j equal 1, that should be the trivial case, where it says exactly that the size is at least square root. That's what this says in that case. So this is a far-reaching generalization of that assumption. A little later, Frankel and co-authors proved that if we assume 4-wise intersection, then we have actually n to the 1/3 in the exponent. That wasn't there in the previous paper. And what Ellis and Narayanan now proved was that if we have 3-wise intersections, okay, so this is exponentially decaying, moderately exponentially. By moderately exponential, I mean that the exponent is not n, but it is a power of n. However, what Ellis and Narayanan proved was a much weaker decay. They proved a polynomial decay. So they proved that the proportion of sets in a 3-wise intersecting vertex-transitive hypergraph is going to 0 at a polynomial rate. Here is the main tool. So the main tool really comes from things that people studied in the theory of Boolean functions, especially influences of Boolean functions, and that is the tool. The entire proof, based on this, the entire proof is just 5 pages, so it's a short proof. Okay, all right. So this is the result that Ellis and Nayaran have, and this is the conjecture that they are making. The conjecture is far stronger. Their conjecture is much stronger than what Frankel and company was able to prove about four-wise intersection, and obviously four-wise intersection condition makes the decay faster than three-wise intersection. But they conjecture that the essentially trivial lower bound is actually the upper bound. Now, why is this a lower bound? That's straightforward, because we can just take simply the three-dimensional projective space over a finite field and then look at all those subsets of points in that space that contain a hyperplane. So in 3D, if they contain a hyperplane, they are three-wise intersecting, and this is the number you can count. And obviously, they inherit the symmetry of the projective space, which is then vertex-transitive. Okay? So that's the conjecture, and that's what is known. So this is a challenge to everybody who likes to look at a big, that's what I like, look at a big gap in knowledge and then try to attack that. You know, if the gap is a constant factor, who cares? So, all right. Okay, so back to now the question. Okay, so this was the third question. Can we make inferences from regularity that would, oops, do I need to take a break now? Okay. Or how's time? Yes? 50 or so. So maybe this is a good time for me to take the break then. Yeah.